All right, let's get started. So last lecture we talked about the signals, the type of signals that you have, discrete signals, analog signals, discrete in time, discrete in value, the differences between them, the applications of, let's say, some basic electronic circuits. And we had a discussion on why we need nonlinear elements. And today we're going to expand on it a little bit. Then we also saw that a lot of the material that you know about electric circuits, about let's say analyzing electric circuits, they are transferable to electronics. We need to learn a couple of new techniques, but for this course to succeed in this course, you definitely need to know how to analyze basic circuits. And we quickly overview some of the laws and methods that you learned in electric circuits to analyze linear circuits, and overview them quickly. But for the rest of the semester, I'm going to assume that you know how to analyze these circuits, so we're not going to review, for example, KVL and KCL laws anytime in the future. We're just going to apply them to the circuits that we are analyzing. So, as I just said, and you probably recall, we have two fundamental laws that come from physics that we use all the time to analyze electronic circuits or electric circuits. The first one is Kirchhoff's current law, or in short we write it as KCL. And KCL basically says that the sum of the currents that enter or leave a node is zero, or the sum of the currents that enter a node in any circuit and those that leave that node is zero, right? So, for example, if you have any circuit that looks my device is not working well. All right, so last lecture we talked about the types of signals that we normally deal with in electronics. We talked about the differences between electrical engineers or electrical circuits and electronics circuits, and we said in electronics we're mainly dealing with nonlinear elements. And then we had a look at a couple of examples in real world around you to see when you need electronic circuits, why you need electronic circuits. And today, in this next maybe half an hour or so, I'm going to review some of the circuit analysis techniques that we learned in our electric circuits course. These are applicable to electronics, mostly to the whatever that you learned in electric circuits. if we are dealing with a linear circuit, is directly applicable. Some of them are just techniques that you can use for linear circuits, and we have to be a bit careful in using them. And today we review those techniques a little bit together, just maybe solve an example or two with them, and then go and learn about the first nonlinear device that we have in this course, which is a diode. So the first circuit analysis technique that I'm going to talk about today is the Kirchhoff's current law, or KCL for short. KCL says that if you have a circuit, it doesn't matter if it is linear, nonlinear, whatever type of elements you have, all those kinds of, so this could continue in either direction. It says that when you have a circuit, if you look at a node in that circuit, the sum of the currents to any node in the circuit is 0. So if this is I1, I2, and let's say I3 in that direction, it says that I1 plus I2 and then I3 has a negative direction, I3 is 0, right? Or the other way of stating it is that it says the sum of the currents that enter a node is equal to the sum of the currents that leave the node. And this makes sense. So actually, I'm going to ask a question from you, the remote audience here. And I'm going to keep doing this. I did it for the first half of the lecture and I paused for a while. What I'm going to do now is that from now on is that I ask you a question, a short pause. You can pause the video, think about it for a second, and then play the rest of the video. So the question now is that why do we have KCL? What will happen if the sum of the currents that enter a node is larger or smaller than the currents that leave that node? So just think for about a second for why this should be the case. It's a physical law. And the answer is that, well, we all know that current is moving charges, right? So basically the number of charge carriers that you have per second gives you the value for the current. So if the sum of the currents, let's say, that enter a node, let's say, is larger than the sum of the currents that leave the node, then the number of charges that are coming in is larger than the number of charges that are leaving that node. So you're going to have charge buildup in that circuit, and that doesn't happen, right? So in any circuit that you have, you don't really have charge buildup. The current keeps flowing through the circuit. So this is coming from the conservation of charge. The second law, oh, actually, and one more thing here is that we are talking about a node here, but KCL actually applies to any cut set in a circuit. So for example, if you divide this circuit, so let's say this is our much bigger than what I'm showing here circuit, and you come up with a cut here. So let's say this cut that divides this circuit in two parts, two separate parts from each other. Then you can always say that the sum of the currents that leave that cut and the ones that enter that cut are equal. And it doesn't matter how many branches you go through, and again, it's because of the conservation of charge. The second law that we used all the time, or we learned in electric circuits, and it's as popular or as useful in circuit analysis as KCL, is KVL, Kirchhoff's voltage law. And this is different. This says that if you have a circuit of whatever complexity, linear or nonlinear, and you find a loop, if you go around the circuit and come back to the same starting point, let's say this, and let's put the current source here, and I don't know, a resistor here, right? So it says, a circuit like this has many loops, but if you take any of these loops and go around that loop and come back to the same starting point, so it could be this, or it could be, for example, this loop, this larger loop, right? If you go around that loop and come back to the same point, the sum of the voltages that you have is going to be 0. So for KCL, the sum of the currents that enter and leave the node are 0. For KVL, the sum of the voltages are 0. So if I call this, let's say, V1, let's say this is V2, and let's say I choose this to be V3. So if I go around that loop, it's V1 plus V2 minus V3 is 0. So that's what KVL tells us. And now the question I have to you is that why does KVL hold? What do you think is the physical reason behind KVL? And the answer to that is that, electric potential is a, let's say, manifestation of the amount of energy you have, right? So electrical energy is charge times the electric potential difference. So what happens here is that if you take a charge, arbitrary amount of charge, and push it through this loop and come back to the same location, because you're at the same spot, your energy should be the same. You start from that level of energy, go around the loop, come back to here, you should have the same amount of energy. And therefore what that means is that Q times all those voltages as you go around this loop and come back to the original position, Q times all of those voltages is 0. And therefore, Q is a constant, it's an arbitrary value. What it means is that the sum of those voltages should be 0, right? So now let's go quickly through an example. I will have more detailed examples during our live sessions if there is basically any interest from you. But for now, let's just go through a quick example and apply these circuit analysis laws to one circuit. So this is from your slides. You have this in your slides. The circuit is something that we will see actually later on quite a bit, something like this. But for now, just treat it as a regular linear circuit. Note that KVL and KCL apply to both linear and nonlinear circuits. So what I want to know is the voltage at this node. I'm going to call this RE. Let's call this guy R pi. Let's call this source GM pi. And V pi is the voltage across R pi. So let's just put it here. So this is the resistor. And this is my input voltage, okay? Now, so I want to solve this circuit and figure out what the output voltage is. Just one thing to note here is that in electronics, we're dealing with fairly complicated circuits. You have, you may easily have tens to maybe hundreds of nodes in a circuit. Even in an analog circuit, you may have tens of nodes easily. And as many loops or even more number of loops, right? So what happens is that if I want to draw everything properly connected with the loop and all that, this circuit will look like this. So it's going to be like that, right? And then I have all my loops and everything else. But as it is the norm, and you probably have seen this in your electric circuits, we usually pick a node in the circuit and we say this is our ground potential, this is our zero potential, and we measure all the voltages with respect to that point. So instead of dealing with voltage differences between different nodes and all that all the time, we say, we are going to pick this node, in this case, let's say the bottom of this RE, as my reference point. I'm going to measure all the voltages with respect to this point. So I'm not going to talk about potential differences anymore. I'm just going to talk about potentials, right? So the voltage at that node V out, yes, in reality, it is measured with respect to ground, but I'm just going to say this is the voltage at this node, and I already know that this is my ground. I've let people know that I've chosen this node as my ground potential. And once you do that, then if you have a loop, the bottom of the loop connected, let's say to your chosen ground level, you don't draw those lines anymore, right? So you just make your connection to ground here, make your connection to ground here. What it physically means is that they're actually connected to each other. Same thing for that other branch. And we do this with nodes that are used a lot in your circuit. So in this case, ground is usually one of them. You have a lot of ground connections throughout your circuit. But you also have connections to, let's say, positive power supplies or negative power supplies, as we will see later on in your courses, in this course. And then, if you have, let's say, 10 connections to the positive power supply, I don't go and draw a line and connect all those loops to the positive power supply. I choose a label and I say, this is VCC, 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 and so on and so forth. Now let's go and analyze this circuit. I can use KVL or KCL. Let's just use KCL for now. So KCL says, if I pick this node for my analysis, which is basically the same as this node, right? It says that this current plus this current plus this current should add up to 0. So let's call this I1, I2, I3. So I1 plus I2 plus I3 should be 0. I3 is leaving the node, and I1 and I2 are entering the node. So I1 and I2, the currents that enter the node, should be equal to I3 that is leaving the node. And from circuit theory, I know that the voltage and current relationship for a resistor is basically V is equal to IR. So what I can say for I1 is that I1 is going to be the voltage at this end of the resistor minus the voltage at the bottom of that resistor divided by the resistor value. So it's V in at the top minus V out at the bottom divided by R pi, or you can call it V pi over R pi. It's V pi because we named the voltage drop across that resistor V pi. Plus I2 is the current coming from this controlled current source. So I just write down the value, GM V pi. And they add up to the current 3, which is V out divided by RE. Okay, and I already see in my circuit that V pi is equal to V in minus V out. So plug V pi from here into the equation in the above, and you can find a relationship between V out and V in. So if I want to expand on that, it's just going to be V out times 1 over RE plus GM plus 1 over R pi. So I put all the V outs on the left side is equal to V in, and on the right side I have 1 over R pi plus GM. Okay, and then from here I can find V out as a function of V in. So V out is going to be V in times 1 over R pi plus GM over 1 over RE plus 1 over R pi plus GM. Okay, and we now consider that circuit to be solved. If you have values for RE, GM, R pi, you go and plug them in and basically have a numerical value for that coefficient. One thing that will happen in this course, and you will notice that as we go on, is that in most cases we don't really know the value of V in, right? So in electric circuits, you solve the circuit with a 1 volt input voltage or a 10 volt input voltage or a 220 volt AC voltage or things like that, right? So you usually knew what your input voltage was. In this case, we actually, in most cases, don't know what the input voltage is, right? It's a signal that is coming from an antenna. And if the source is far from you, the signal is weaker. If it is closer, the signal is stronger. You usually don't know the input voltage. You just use V in to represent it, hopefully with some known, at least, let's say, statistical properties for that V in. And then you calculate the ratios of, let's say, different voltages in your circuit to that input voltage, or currents to that input voltage, or input signal in general, and then go and solve the circuit. Now, if I want to solve the same circuit using KVL, then I have to do a little bit more work in this case. So now I notice that I have one loop here, and notice that I start from ground, go into, let's say, through V in and R pi and RE and go to ground. But my loop, I know in the back of my head that is actually closed like that. So this is not an open loop, it's a closed loop. And then I have a loop here. Now, what I notice is on the right loop, so let's call this loop 1 and loop 2. On the right loop, I have a current source. And when I want to write KVL, I need to add up the voltages across different components. But with a current source, I cannot really do that, right? So it's like the current to a voltage source. An ideal voltage source can provide any current that the circuit needs. And same thing here. An ideal current source, which we assume this one is, can sustain any voltage drop across it. So in this case, maybe a KVL on the right loop doesn't help me much, but let's just go through the example and we'll see that we actually can solve it just with the equations from the left loop. So KVL in the left loop, I'm going up this voltage source. It tells me that minus V in plus V pi plus V out is 0, right? So V pi is the voltage drop across this resistor, and V out is the voltage drop across RE. So that's the KVL that I have. But what I can see is that V out is actually I1 plus I2. That's I3. I1 plus I2 times RE. And I also noticed that I2 is GMV pi. It's a current source. Its value is fixed. And I noticed that by combining these, now I have V in is equal to V pi plus I1 is going to be V pi over R pi. I2 is GMV pi times RE. Okay? So this equation gives me V pi as a function of V in easily. So from here, I have V pi is equal to V in divided by 1 plus 1 over R pi plus GM times RE. Okay? And from this equation here, if I put V pi in that equation, I already have V pi as a function of V in. I have V in and V out in that equation. Plug this into that equation, and you should get the same result that you got here. Right? The final answer should be the same no matter the method that you choose. In this case, KVL seemed a bit longer, and in many cases that may actually be true. So you will see that in this course we use KCL more often than KVL. You have to know both, because there are cases that the KVL solves the problem more easily than the KCL. But one of the reasons that we use KCL a little bit more often than KVL is that in KCL, you're talking about the sums of currents, but those currents are usually related to the voltages at those nodes. So as you can see, for example, in the solution in the above, when I'm adding up currents, I'm actually adding up something times the voltage. And in electronics, voltage is an easier variable to deal with than current. They go hand in hand. You always have voltages and currents together. But I'm a bit more comfortable with voltages. And the reason for that is that voltages are easier to measure for me. So if I want to measure a voltage in a circuit, I've built a circuit and I want to analyze it and I want to make sure that it is working well as I designed it and things like that, all I need to do a voltage measurement is a good multimeter or a good oscilloscope. I put my probe at the node that I'm interested in. The other probe is connected to the ground potential, and I take my measurement, and I can go and measure the voltage at any node that I want in that circuit. Measurement of a current is not that easy. In most cases, to measure current, you need to actually open up the circuit, put your sensor element in there, a current meter in there, because the current is measured in series with that branch, right? So you have to put your instrument inside the circuit. And first of all, that's a little bit inconvenient. You have to open up the circuit, put the current meter in there and then do the measurement. And then if you want to go and throughout the different branches in your circuit, things may not actually even be possible, right? So if you're dealing with a circuit that is already on a PCB, you cannot open up those tracks and do a measurement on them directly, right? So in most cases, that's actually not even possible, because it could be a track that is on the third layer of a 4-layer PCB. But voltages you can always measure. As long as you have a view of that track, you can put your probe in there and measure it. So because they're easier to measure, it's easier to get an insight about how the circuit works and if it is behaving properly if you're dealing with voltage signals. Now, on the next slide that you have from the lecture slides, I'm showing you a not so complicated analog circuit. So this is an op-amp circuit. You see that you have about 20 transistors here. And if I want to start writing KVLs and KCLs to solve this circuit, the equation, the system of equations that I will have will be just too complicated. And my human mind and let's say my limited lifetime doesn't allow me to solve those kinds of circuits or too many of those circuits. A computer can be just fine. You can give this circuit to a computer as long as you establish rules for the computer to basically draw or write up the KVL and KCLs automatically. They can just go and create that 10 by 10, 20 by 20 system of equations and solve it and spit out all the values for the voltages and currents in that circuit. And that's how actually software like SPICE work, the circuit simulators work. But for me as a human, that is going to take too much. Not only it's going to take too much, but there's also a good possibility of making a mistake somewhere, right? So if you have a 5 by 5 system of equations, 5 variables that are independent from each other, it's not unlikely that there could be a, let's say, missing sign somewhere. So you miss a negative sign somewhere, and then all of a sudden all your values will be wrong. And if you're unlucky, it may not be that easy to detect. So the other point is that, in a circuit like that you have tens of transistors, usually an experienced circuit designer, which hopefully you will have, let's say, some familiarity with them by the end of this course, can break the circuit into multiple stages, right? You can look at this complicated circuit and say, this combination of devices are your input stage, this combination of devices is your middle stage, and the last one is your power amplifier. The first one, you want to have a lot of gain from it. The second one gives you more gain. The last one gives you a lot of current. And in most cases, you just want to focus on one of these stages at a time, right? So you want to, let's say, focus on the power amplifier stage at the very end of this chain, and the rest of the circuit is not of importance to you. It is providing the input signals to the last stage, but you're not concerned with how they are operating. So what you want to do is that you want to simplify the rest of the circuit, whatever that is behind your stage or after your stage, and just keep your focus on whatever that you're interested in.